Hello! We're a team of 4 computer science students at SUNY Albany, advised by Dr. Brian Ruttenberg from Google, and we're working on implementing machine learning techniques in product classification. The overarching goal of this project is to analyze different methods that can efficiently and effectively categorize or classify various products online. Online retail is quickly becoming the dominant method of shopping for many consumers, which puts pressure on sellers to format their listings as efficiently as possible. As such, their goal becomes categorizing items for sale so that consumers can find them quickly online. For shops with relatively few items, this isn't too much of a problem. However, for larger operations such as Walmart or Amazon, it can prove costly, both in terms of time and manpower. This solution has a goal to automate as much of the process as possible while retaining an acceptable degree of classification accuracy.
Recently, there has been research being conducted on implementing machine learning into product classification. One such method uses Bayes' theorem, a probabilistic approach, to determine whether an item is likely to fit in a category. Furthermore, text processing features like stemming, number removal, and word removal have been used. This method can be difficult to implement, however, since it requires a prior knowledge of each dataset, which we might not have when training the program on something it's never seen before. In addition, it has also shown to be less accurate than other methods tested, since it assumes statistical independence between the features, which is almost never true in practice. One additional method takes a middle road between the previous two. The program tries to use probability to ascertain the product's category and determines a numerical measure of confidence for its guess. The programmer then sets a confidence threshold, allowing the program to pass on the product to human eyes for manual classification if the minimum confidence interval is not met. The major drawback for this method is that it does not guarantee completely automatic classification.
In addition to the prior work, our goal in this project was to experiment the following 4 machine learning methods. The naive Bayes classifier involves looking at each word in the product name independently, determining the likelihood of it belonging to each category, and choosing the category with the highest probability. For logistic regression, the classifier uses the product's name to determine probabilistic thresholds for each category. Decision tree predicts the classification accuracy by learning simple decision rules inferred from the data features, while using aspects such as tree depth. Finally, we use support vector machines, known as SVMs, which very basically involve using hyperplanes to split objects based on category, and determine the closest support vectors on either side.
In the next 3 slides, we've listed the size of each category in the 3 datasets that we used in our experiments. The first is the largest, and contains items from an online French boutique called New Chic. New Chic's dataset has a total of 9 classes, making up a total of around 75,000 products. The second dataset we've used for training and testing is a dataset from one of the world's largest retailers, Walmart. As you can see, the class size for each dataset can vary substantially. For example, in this dataset, the sports and outdoors category towers over the rest with more than 2 times the products of the category right after it. This imbalanced dataset presents its own issues, which we'll provide attempts to remedy in a later slide. Finally, our last dataset comes from the largest online retailer, Amazon. For each dataset, every product includes a category, subcategory, name, price, and brand. To include the latter 2 features in the classifier training process, we appended them to the product's name so that they were included as a part of the bag of words model that we'll create.
Imbalanced datasets present a problem. If we train a classifier on a set that is skewed towards one category in particular, it can disproportionately favor that category in its predictions, which would negatively affect our accuracy. So what's the solution? We found 2 solutions to help deal with this problem. First, we removed categories with less than 200 products and added those products into a newly created miscellaneous category called Other. This method helps reduce the level of imbalance at the cost of some information. We lose the low element categories entirely, so any items that would fit into that category would end up in Other, but there's less risk of misclassification into that category. Since naive Bayes is a generative model, balancing data isn't part of the true process, and therefore the method does not contain class weights.
In addition, we computed the confusion matrix using logistic regression, which helps visualize the performance of the classification model. The diagonal values in the matrix show that the classifier was very accurately labeling the categories.
In order to measure each classifier's accuracy, we needed to have some test values whose categories were known. Our solution: withhold the percentage of data elements at random from the training dataset, and put them into a separate training set. Once the testing values were determined, we stored them so that we could run multiple tests on the same, randomly acquired data to avoid skewed results. When we mention percent of data withheld, testing data is what we're referring to.
Our first research question has to do with the size of the datasets that we're using. This question also pertains to the number of categories and subcategories in each dataset. Here we see a table of accuracies for each of the 4 classification methods we used on each of our datasets. To compute these values, we ran our training method with 20% data withheld for testing on each classification method a total of n times, in this case 20, and averaged the resulting accuracies. As you can see, the logistic regression and SVM methods generally performed best, followed by naive Bayes and decision tree. In each case, we trained the classifier using the product's main categories, that is, not their subcategories. Because each dataset has relatively few main categories, the prediction accuracies are understandably rather high. Classifying on the product's subcategories presents a significantly different result. There are many more subcategories than main categories in each dataset, and each category's subcategories will obviously be related, which can make it difficult for the classifier to determine where a product will fit best. As a result, we can see that each method in each of these plots reports lower accuracy than the previous slide's table. In general, we found that smaller datasets tend to produce lower accuracies. This is largely due to the fact that there is simply less data that the classifier gets exposed to and learns from. We also found that as the number of categories increases for a dataset, it often becomes harder for the classifier to differentiate between them, causing lower accuracies. This is particularly true for categories that are closely related, such as subcategories. These considerations are not the only determinants for classifier accuracy. Additional features, like price, brand, or color, can play a factor, as well as how distinct the data elements themselves are. For instance, one of the products in a dataset included words like hibiscus, which didn't appear elsewhere in the datasets and affected its proper classification.
Our research question simply asks which classifier method works the best. Our primary concern with the classifiers are accuracy, how long it took to both train on the dataset, and predict testing values. This slide depicts multiple plots demonstrating the accuracy of each classifier method on a dataset. The x-axis represents the percentage of data that is withheld from the training data for testing, and the y-axis represents the reported accuracy based on classifying the training data. As we saw before, the SVM method is generally the most accurate, followed by linear regression, then naive Bayes, and finally the tree classifier method. We can see that for all methods, as the amount of training data decreases, the classifier's accuracy diminishes. This is expected because it is exposed to progressively less data to learn on, reducing its ability to predict. This slide shows the same accuracy trials run on the Walmart dataset. We can see that the order of most to least accurate classifier remains the same, and that the accuracy for each decreases as the training data is lowered. These plots demonstrate the time it takes for each classifier method. The x-axis represents the percentage of data that was withheld from the training data for testing, and the y-axis represents the time it takes to classify the testing data. Here we finally see the advantage of using the naive Bayes method. It is by far the fastest training method, followed by the linear regression, then tree, and finally the SVM method. As seen before, the same patterns are represented for the Walmart data. We can see in each case that while it boasts a very high classification accuracy, the SVM method takes much longer to train compared to the other methods. What we ultimately glean from these graphs is that the SVM takes the most time to train and predict, but produces the most accurate results. Logistic regression takes slightly more time to train than the tree classifier, but produces the second highest overall accuracy. As we've seen, the least two accurate methods, tree classifier and naive Bayes, are the ones that take the least time to train and predict. These observations can have immediate practical use. If someone wants to train a classifier on a dataset with 1 million elements, and they don't have a supercomputer or a very long time to wait, they'd likely have to do so using the fast training naive Bayes method.
Our third research question focuses around the dependency of training one dataset and testing the resulting classifier on a different dataset. More so, how accurately does a classification method classify on datasets other than the trained dataset? Predictably, the answer to this question depends on the datasets involved. Because the Newsheek and Walmart datasets each had similar categories such as home and beauty, We were able to train a classifier on one of the datasets and use products from the other dataset to test. To obtain the topmost results, we trained a naive Bayes classifier on the new Chic dataset, and then passed all products that were in the same beauty category in the Walmart dataset into the classifier. The bottom image shows the same test, but with a house category instead. These tests were run 25 times each, and the percent of products guessed correctly were averaged to find the final accuracy. The classifier guessed the beauty category correctly about 40% of the time, while it guessed the house category correctly about 90% of the time. While these tests were run only using a naive Bayes classifier, we intend to run all 4 methods in a similar manner and include those results in our final report. In contrast to the previous slide's results, we found that reversing the training and testing datasets produced extremely low accuracies. Training the classifier on the Walmart dataset and testing the prediction of the beauty and house elements from the new Chic dataset yields only 0.053% and 1.357% accuracy, respectively. Looking at all of the results on the same screen, the immediate question that arises is, why is training one dataset and then testing using a different dataset so inconsistent with its accuracies? There are 2 points that we can take away from this experiment. 1. Training one dataset does not signify that the model will act the same on datasets other than itself. Furthermore, we believe that the accuracies of these methods may depend on if the testing dataset can be a subset of the trained dataset. That is, if most of its categories are similar to ones in the trained dataset. We hope to expand further on this in our final report.
This brings us to our last research question in our study. How robust are the classification methods? In order to measure the robustness of the methods, we set 2 experiments with our datasets. Our first experiment involved appending a string to the front of every product in our dataset and observing the changes in accuracy for each classification method. For analytical purposes, we only focused on the New Chic and Amazon datasets. The graph on the left depicts a New Chic original dataset with no alterations, and the graph on the right shows the changes after a string was added in the beginning of each product name. As you may notice, the accuracy and trends remain around the same. There aren't many differences. The results for the Amazon dataset are quite similar for each method, though the naive Bayes and tree classifier methods appear to experience a slight increase in accuracy. Let's test the robustness in a different way. What would happen if we took the top 10 most common words in our dataset and omitted them completely? On the bottom left, you can see the top 10 most common words that appeared in the dataset, as well as the number of times they appeared in our New Chic dataset. The graph on the left includes the accuracies for the unaltered dataset, and the graph on the right shows the accuracies for the new dataset with all instances of the 10-word list removed from the product names. We can clearly see a decrease in accuracy for linear regression, naive Bayes, and tree classifier methods, and a slight decrease in SVM. This makes sense, since those 10 words are most likely for classification in these datasets. For example, if you take a look at the list includes words like men, bags, and women. All these 3 words are actually categories in our dataset as well. Like the previous slide, this slide shows most common words of the dataset from Amazon and how many times they appeared. However, unlike the last dataset, the trends and accuracies remain nearly the same with or without the common words trained. Looking at the listing of the omitted words, we find that this result makes sense. Words like the, of, and with aren't likely to help the classifier determine what category the product should fit in. Since they're less important for determining the product's category, their omission doesn't have as much of an effect as an accuracy as we saw in the New Chic dataset. To summarize, we found that prepending a string to each product's name doesn't really affect the accuracy of the classifier. On the other hand, subtracting words from the product's name can have a pronounced effect on the accuracy depending on how important that word is for classification. The next couple of slides mention our individual contributions for our project. Thank you. Please feel free to reach out to us if you have any questions or comments about our research.